Okay, good morning to you. And we start the second week, spring 2003, Math 70. And just to cover a few things in terms of where we were at the end of the week, we finished up covering section 2.1. We're going to be in 2.2 today. And just a few updates on some things that will be available this week. The video tutorial section I worked on over the weekend. I spent about 10 hours watching me and didn't throw a brick through the screen, so the overall perception was there are a few places where I would have liked to have done things a little bit better. But the links have been created. I'm in the process of getting that web page up, hopefully this afternoon, depending on interruptions. It was going to be done last night, and as was the case so many times during the week, Murphy was alive and well. I had reached a point where the computer I was using, it's the one I did the presentation on Friday in here, and I decided to try to see if I could get it to behave a little bit better. So that means you look at the hard drive, which is a little like a messy bedroom. And think of going into a bedroom with a bunch of 2-year-olds who've left toys all over the floor, and you go in and try to organize it and create some space. Well, much the same idea. And so far, as of this morning at 6 a.m., it was 24 hours into the defragmentation process and still had not completed. And my understanding is that given the lapse of time I had allowed, which was substantial, 30 hours would not be unusual. So that sort of got in my way. I thought, okay, 5 hours, double it. Why not? That'll put us at 10, and I'll still have time to get everything written up last night. Well, I went to bed last night 14 hours, 15 hours later, and this morning it still wasn't done. So I'm going to have to punt and use a different computer today, but nevertheless should have video tutorials up. And what I'm doing is isolating on topics, things like the community property or the properties, the real number system, and indicating a clip that you can watch from the lecture content we've done to give you some help on a 24/7 basis, meaning 24 hours a day, 7 days a week, if you have a connection that allows you to watch video. Now, if not, a 2-minute clip may take you 5 minutes with congestion and buffering, but it's certainly not too bad compared to having to do a whole hour that way. One of the emails I had this morning from somebody watching this as part of the group watching the videos involved problem 9 from section 2.1. So we'll start looking at a homework problem that was requested. I didn't have any requests at 6:30 this morning on voicemail, so I'm going to assume this was the only serious problem for those of you watching the presentations on the video. We're going to cut to the document cam. And this is the solution I wrote out just a few minutes ago as I prepared for what we were doing. And the original problem is given at the top of the presentation there. And I subtracted, in essence, 7/5 W from both sides and added 6 to both sides. And I didn't show that step, but that was the process. Now, the 2W over 5 minus 7/5 W, if you take this particular line and you think of taking the W out using the distributive property, you would have W times 2/5 minus 7/5, which is negative 5/5. That becomes negative 1. And then we have negative 1W equals 6. That implies that W must be negative 6 if the inverse of W is 6. Now you could think of multiplying both sides by minus 1. Now I'm going to slide this up, but first the comment I'm going to make, in what we're doing right here, my approach was to get the variable on the left side. That's fairly standard process. But there is an alternative solution. I'm going to slide up so you can see the alternative solution. And that is to take the original 2/5 W and think of subtracting 2/5 W from both sides. That leaves me the negative 6 on the left side. The expression on the right side just becomes 5/5 W, which is W. Now, minus 6 is equal to W by the commutative property. Now, I want to state that differently. It's like a commutative property, but it's not a commutative property. It's called the symmetric property of equality. If A equals B, B equals A. So you can go from here to here immediately. You get the same solution in both ways. As a rule of thumb, I'm inclined to encourage you to get the variable on the left side immediately and operate on that basis. Now there's a little presentation in 2.1 just prior to the exercises that deals with this particular problem, and it's in the top of page 95. And it reads here, if minus x is equal to a, then x is equal to minus a. Now let me scroll over a little bit and see if I can get the lighting better. So if minus x is a, then x is minus a. Now the argument for that is by the inverse. Basically you can say if the inverse of x is equal to a, then x itself must have been the inverse of a. That's another way of saying it. That would be the logical argument for making that a correct statement. So if you have minus x is equal to something, then x is just minus that something. And I don't think you need to make a major issue out of it. Again, it brings up the question of what is an optimal procedure. Is there one way to do the problem? Typically, the answer is no. The key is to make sure that what you are doing is verifiable, that each step you could defend through one of the 11 properties, one of the properties of equality. Now, we talked about equality in terms of a well-defined property of equality with respect to addition and multiplication. And that's where I'd like to start and extend that a little bit to what we call a reflexive, symmetric, and transitive property of equality, just so that you are aware of what we argue about having an equal sign. Now, I might comment there's a difference between saying two things are equal as numbers and that two equations are equivalent to each other. Now, it's not a subtle difference. It's one that you need to be understanding. If I argue that x plus 2 equals 3 can be simplified to x equals 1, I'm saying those are equivalent equations because they have the same solution. But when I say that x equals 3 and then say 3 equals x, I'm talking about equality and a property of equality. So as we go to this left side of the board, I believe your text and authors use big A and big B for A equals B for real numbers. Now the argument is that A is equal to B. If that's true, then this implies, and notice this is not an equal sign, this is an implication arrow. So this is implying that B is equal to A. Now that's referred to as the symmetric property. There's a symmetry, so you can say A equals B or B equals A. The reflexive property is a fairly obvious one, that A is equal to itself. We call that the reflexive property. And then the transitive property for equations is if A equals B and B is equal to C, then what can you say? A is equal to C. So I'm writing this as an if-then step, an implication. That's what this is another way of interpreting here. If A is equal to B, then B is equal to A. So I'm using the arrows here to imply. Here I'm actually writing an if-then statement. So this would say A is equal to C. So reflexive, symmetric, and transitive. And the property that I used in the solution where I said I had minus W equaled 6 and then went to W equals minus 6 is not either of those two or three properties. That's by inverse. But when I said that in one solution I have minus 6 equals W and then I wrote W is equal to minus 6, that's using the symmetric property. There's a subtlety there. This is by a property of equality. This is by the inverse property of the real number system. So this used by inverse property of real numbers. This was by the symmetric property of equality. And it's just to be aware of what's allowing you to make a statement. Laura?
If we do our homework the way that you showed the one up there on the screen, is that acceptable?
Yes.
So we don't have to do it on both sides, like, you know?
Oh, I see what you're asking. Okay, maybe. Okay, let's come back to what I did in the screen, where we're talking about this solution. Is this correct?
Yeah.
Okay. Now, can you do that? And I think what you're asking, as opposed to showing the addition of the same number to both sides. That is, I could have embellished this. Let's come off there for just a minute, Debbie. I could have embellished this by saying, okay, plus negative 7/5 W. I'm going to write this out so you can see it here in just a moment. Okay, let's look at what we have now. So I physically show that I'm adding negative 7/5 W to both sides, which then becomes the new expression. This one is simply through the distributive property. The rest just follows. So the question, oh, hold on, I still had another step, didn't I? Because I added 6 to both sides. So then I took the results of this first step, and then I added 6 to both sides and sort of went down to here in one step. That brings up a question again of, in this introductory section, 2.1, I think the author's intent is to show the additions. And as I mentioned to you in my presentation, I have mixed feelings about that, because if we start as a process where you have to show every time you do the problem what you've added to both sides, and you get into that as the only way you can approach the problem, I've done you a misservice, because you are just never going to pick up the speed that is necessary to do things mentally. To allow you not to write out what you've added on both sides gets us to the point where maybe you're doing operations and not understanding them. So my answer to your question is, find a middle ground for yourself that provides, in some problems, the clarity, but don't let it become a kind of tedious exercise that just keeps you from getting the solutions. I don't know where that balance is for each of you, and I'm not going to be too critical in this problem set. What I need to have you understand, total liberty and showing nothing but just moving things around. Let's go back to the problem where I went from the first line to the second line and basically did 2 additions. To go there and not ask you to document that starts approaching that process that is involved where you do things and in doing them can't explain why. That's a little bit of a concern. There's an interesting little historical vignette that relates to Laura's question indirectly. And that vignette has to do with understanding where the word algebra comes from in terms of derivation. So let's go to page 95. Okay. This is talking about a rind papyrus. And originally, and boy, that's not coming out very good at all. Let me darken a little bit. Boy, Debbie, okay, I guess shading it helps. Let's come off there for a moment. There's an effort here to cover 2 things. One, most of you are familiar with the word aha. Is that door closed? Can you make sure it's closed? It is. We're just getting, there we go. As we come back to the book on page 95, we've all said aha about something where you understand. Aha, it's whole, meaning aha is like X. So that was an interesting little piece of information. But then coming down to the work of, and I don't know if I'm going to pronounce this properly. Let's go to the word, the phrase. This is a person's name, Al-Khwarizmi, and I'm sure I'm not doing that well. But he writes a book, and the text in Latin, okay, became Aljabr, which if you were to state it, you would say what? Algebra, and hence algebra. So that's the argument of where we get the phrase algebra. But note, the translation means the science of transposition and cancellation. Transposing and canceling. Now, let me explain that in a little different way. If I take 2x plus 2 equals 8 as an equation. And this is coming back to Laura, sort of that idea, what do you do as opposed to what you have to explain? The argument is you could add negative 2 to both sides. In the days when I learned algebra, we talked about transposing the 2. We just said if the 2 goes to the other side of the equal sign, it becomes negative. So this gave you 2x equals 8 minus 2, so you immediately transposed and had this. So you transposed a 2 and got 2x equals 6. The transposition. And then we said if 2x is equal to 6, divide both sides by 2, you canceled and you immediately got x equals 3. And so we would write it in terms of 3 steps. So you had transposition and cancellation. And that is the mechanics. So we can think of this as these are the mechanics of doing algebra. But from a conceptual point of view, do you understand what's involved? And there's a subtlety there because understanding what allows these steps to take place is what allows you to build on beginning algebra and go on. Now, I think looking at my own background, I learned to do algebra much this way, a mechanical process. But later on, I was expected to understand what was going on, and that was a lot harder for me. And what made it possible for me was the circumstances I found myself in as a student in upper division at a college where I was in a dormitory and the resident mathematician, meaning I was the one person majoring in mathematics on my entire floor. So guess who became the tutor for anybody who had a question about mathematics? And I would be asked questions such as, okay, I see that we go from here to here, but why does that work? Why do we do that step? Other than to say, just transpose. And I found myself having to explain things that I had never made any effort to understand. I just did them. And so that is what a modern curriculum is trying to avoid. Doing things without understanding. Now the downside of that, you do so much explaining you can't get anything done. There's a balance. This first set of problems, try to find a way of doing it to where you do enough documentation, you're convinced you understand process. And as we go into today's homework, I think it'll be a little bit more of the issue, okay, simplify things, do them, and be efficient, much as I've done here. Okay? So mechanics versus understanding. There was an interesting parody about what was called the new mathematics that occurred in the 1960s. In the 1960s, there was a concern that students were doing things in algebra and having no idea what they were doing. And so the emphasis during that period of time became rewriting the curriculum so you understood the process. And this book reflects that change. The parody that was given, in this case, by Tom Lehrer, a mathematician out of Harvard University that's still teaching and usually visits Santa Cruz during the springtime, but was doing stand-up comedian stuff with piano at places like the Hungry Eye in San Francisco at the time. And he did a parody in the New Math, which said, it's not so important that you get the right answer, but that you understand what you're doing. The parody, we've traded in accuracy for understanding. And it's difficult to achieve both. That's the balance this text and others try to achieve. So with that said, as we answer the remaining questions in section 2.1, if you're asking, do I have enough detail? Certainly I expect minimally the problem, some intermediate steps in general, and then an answer, and I want something as a balance. That's a long-winded answer for Laura's question. Other questions from the homework? Okay.
27.
27.
Got it, but I don't think it's right.
Okay, so it's not a question of getting the right answer, it's did I do the process correctly? Okay, let's see, I have that a little bit too high, see if I can hit, see that? Still, okay, I think, Debbie, that's not too bad. Here is my equation in 27. Now, by the way, what makes this a more difficult problem in general? The decimals involved. So, as I look at that and ask the question, what's the first thing I'd be inclined to do? Simplify the left side. So I have 5.2q and a negative 7.1q. The question, do I need to rewrite the left side so that I've used the commutative property and the associative property to get all those together? That's an interesting dilemma that we face. So what I'm going to do is rewrite that equation on the board, and let's look at our alternatives. So as we come off that, and let's see if I can get a tape under here and flatten this out with another tape. Okay, Debbie, let's try putting the problem up there again, mostly for me so I can see what I have on the monitor. I have a 5.2q, and then I have a negative 4.6, and then I have a negative 7.1q, and then I have that equal to a negative 0.9q, and then is it a negative 4.6 or 0.46? 4.6. Okay, now we can come to the board. Now again, this is number 27. Now the balance. And by the way, what is the one thing, if you read in the text, that you're encouraged to do here? Before you simplify. Before you combine like terms. Still another little shortcut encouraged.
Solve each equation.
Multiply everything by 10 and get rid of the decimal. Well, okay, but if you want to get it out of the difficulty level of a decimal, you are encouraged as a possible shortcut. Multiply everything by 10 and you no longer have decimals, and that makes it more comfortable for some folks. You don't like that, I can tell. Okay? Now the question, I guess I would be inclined, without showing the commutative property and the associative property, just rewriting this as a step. This is that in-between ground that I was referencing. Then immediately go to the next step where I just combine these two and get a negative 1.9. So I would go to here, and this may be certainly more than I'd be inclined to do if I were just doing this on my own. But what now is very obvious. If I add 4.6 to both sides, the numerical part is out immediately. I don't know if it's necessary to see that, but certainly this might be a nice in-between step. You added 0.9q to both sides and added 4.6 to both sides and immediately get to this. Then this becomes negative 1q equals 0, so negative q equals 0. So q is equal to negative 0, which is 0. Now you may even argue that is a bit tedious. But I think if you cut too far back from there, you're not giving yourself the benefit of what's happening as you carry through the solution. Now, what steps might be possible that you could delete? I think that one could be deleted. Beyond that, I think you're going to find it a little bit tough. You might have argued going from here to here in one step. And I think, yes, you could do it, but that may not be in your best interest at the moment. Make sure you can walk well before you try running. Okay? You can't afford to go face first in the dirt trying to run too fast in this. So I think that's a balance, and maybe, as I say, you might cut one or two steps off there, but not much. If you went from here to here, that is inadequate. To go from here, again the top, to the bottom with nothing in between, I won't buy. Yes?
Essentially just writing the problem down twice. Right? And that's the way we were taught it.
You always write the problem down. The next step I did what?
Combine. So that's what you
No.
did.
No,
The
you
next
did
step,
it.
I rearranged trying to get these together. Now, I think you could have gone from here to here. I think that would have been a reasonable process. But to go from here to here, or from there to there, and do all that in your head, right now, not advisable. Give me something in between to convince me you're playing the game with the right set of rules. The rules are the things that are allowed by the 11 properties and our definition of equality. Any other question on the problem? Okay, other questions on the homework? Everything else okay? No? Then if no, what is your question?
I was going to ask you to do number 25.
25.
Yes, sir.
Okay, let's go back to the document can. There's our problem, still up there, 25. And in fact, I can try dropping that down a little bit tighter. There's 25, a little bit easier to see. Now, as you see that, I would, first thing, I want the equation written as is. Now, my second step, as you're eyeballing the second line, I would go 13x plus 8 equals 12x plus 4. That's my next line. So I'm just going to write the second line up here for a moment while that's still on the screen so I can read it. I said I'd be at 13x plus 8, and that was equal to 12x plus 4. Now, in my original problem, which is number 25, right, I've got this as my second line. Now the question, how much do you show from there? Well, in a sense, I'm going to subtract 12x from both sides or add negative 12x to both sides. I think it is an addition process from a theoretical point of view, but my head still tends to subtract from a practical point of view. So I have x there. I subtract 8 from both sides and immediately get negative 4, and so I have my solution. Now, the original problem, again, was 6x plus 5 plus 7x plus 3 is equal to 12x plus 4. To do anything less than that is not adequate in your presentation. It has to be that, at least that is a minimum. Original, intermediate step, and answer. And I'd say, given the nature of the problem, that's good. Again, encourage you, maybe every other problem or something, to go one extra step on occasion, where maybe you start with the original. So let me rewrite it again. 6x plus 5 plus 7x plus 3. I'm just restating the problem now. And we're then, in a possible sort of way, saying, this is certainly a no-brainer at this point, doing that much of a simplification. But the next part, I think I'd be inclined to say negative 12x, I'm adding that to both sides, and a negative 8 I'm adding to both sides. And then when I get all that done, I have, this is my solution. So I'm showing what was done. And that little extra bit of information may be enough that you have a clear understanding of what was going on. Again, the difference, trying to get something, first you understand, and then it becomes mechanical. Okay? Now, there are a number of areas that come to my mind as I come back here to the desk. Music and sports. There's technique. And then you try to make it become nearly a matter of muscle memory. But you first do technique and understand why you do certain things before it becomes automatic. So if you are looking at a sport, and whether it's football, soccer, basketball, there are certain techniques that you do, you learn to do, and then you become mechanical. I'm just going to take one that's fairly obvious in all three sports I mentioned. You come up to guard a player. Think of this in yesterday's game. You've got a wide out, an end, who's going to go out and try to catch a pass, and you're defending it. If you're in soccer, same argument. You've got somebody you're basically trying to guard in basketball. If you face them straight on, and that's the way you start your play, you're going to lose a step because you have to rotate 90 degrees and get yourself in a position to take a step. Instead of your feet being square, you back one off from the other so that you can rotate and immediately start your run. Now that's a technique. Why does it work? So you gain the step. Without it, somebody's going to get ahead of you and score. So you learn the technique because you understand why it works, and then you practice it so you don't have to think about it. Okay, it's a simple little idea. In music, there are certain things that mechanically you try to do because it will make it possible for you to build up the speed to get where you want. So for example, if you're playing like a guitar and you get used to anchoring your pinky on the front of the guitar so that you can do your work with either a pick or your thumb, then when you have to do something else that requires that the pinky be off the guitar, if you don't learn to practice that way, then it sounds very badly when you try to do it when you have to do runs that have to be done very quickly. Algebra is the same way. There are techniques. And what we're doing here is trying to develop the technique so the speed will come later. And then you don't even think about it in the heat of a test or doing a problem. No other questions? Okay, pass the homework over again as usual. Make sure your name is on it. And we'll pass it over on the usual side. It's towards this side of the room as I'm pointing. And if you'll pass it forward, we'll get that going and we'll be in business. Okay. Now the question. What are we going to do in 2.1 that's different than what we did in 2.2 that was not done in 2.1? And the answer is more of the above, but more complicated. And this is where now you're supposed to pick up speed, you're supposed to pick up the process, so it's not such a challenge. One of the things I'd like to come back to, Debbie, is we look at the right side of the board here where I have this solution of x equals minus 4. So let's come back to that. Basically what we did was simplify an expression, correct? Got a solution. Now how do you know that solution's valid? What is your argument that x equals minus 4 is a valid solution? No, you haven't checked it yet. How do you know it's valid? What's your argument? That's checking it. Plugging it in is checking it. How do you know it's valid? Just by what you've done. What's your argument? You're telling me how to check the problem. That is not my question. How do you know this should be a valid solution without checking it? Because every step you did is supposed to give you an equivalent equation. What do we mean by an equivalent equation? Definition. Equivalent equation.
Both sides are equal.
That's what an equation is. You have two sides equal. An equivalent equation means they have the same solutions. If A equals B, I can add C to both sides and get A plus C equals B plus C. When I went from here to here, I simply used the properties of the real numbers. So I'm guaranteed that these expressions are still equal on the left, so they have the same solution. Going from here to here, I did what? We talked about, as we look at it in this coming here, I said you added negative 12x to both sides. You added negative 8 to both sides. So you're guaranteed that this equation has the same solution this equation has. That's well, and Debbie, I'm going to go to the left side. So if you can kick over to the properties of equality. Okay. When I was at the properties of equality that we talked about with A equals B, B equals A, remember there were two more. And the two more were that, let's see, A plus C is equal to B plus C, and AC is equal to BC. Those were the well-defined properties with respect to addition and multiplication. I'm guaranteed that if I use these properties and the 11 properties of the real number system as we go to the right side, that these equations that I get have the same solution. That's what guarantees me that if this has a solution of minus 4, so do all the others. So if you do things right, you have that built-in guarantee. Now, how do you check a problem? You take this solution, and now you substitute it for x in every part of the problem in the line. Checking a problem can take twice as much time as solving the equation. Let's see what would happen as I check this problem. I'm going to come down here. I would have 6 times minus 4. I would have plus 5, plus 7 times minus 4, plus 3. I want to know, is that equal to 12 times minus 4 plus 4? That is a mess. Okay, so this is negative 24 plus 5 minus 28 plus 3, negative 28 plus 4. Okay, negative 24, negative 28, and let's see. I make sure I have the problem written correctly. Plus 5, 7x plus 3, and I had 12x, and I should have had 48. Negative 48. I saw the 2. I didn't see the 1. I didn't even see that. I'm not sure how I got that. Negative 48. Now, this is what here? Negative 44 on the right? Now here, negative 24, negative 28, that's negative 52. Negative 52 plus 8 is negative 44. Negative 44 equals negative 44. That takes longer than doing the problem. But that's what checking a solution is about. Sometimes you're lucky. Let's slide over now and look at this one, because this one's a little bit easier. You had q equals 0, correct? Okay, let's tighten it up here. I love q equals 0. So let's bring it in tighter, Debbie, so there. Okay, so this 5.2q, q is 0, piece of cake, that's 0. This is 0, so I have negative 4.6. The right side, q is 0, so that terms out. Negative 4.6 equals negative 4.6, and I'm done. Life is good. Now, there are 4 steps to happiness when you solve a linear equation. Before we go to them, what is a linear equation? Characteristic of a linear equation. What form does it have?
One variable. First degree.
One variable.
And a coefficient.
The exponent is?
First degree. First one.
Understood what? General form, ax plus b equals 0 is one way of thinking of a linear equation in one variable. Ax plus b equals 0. Now to the document, Cam. Now these are the 4 steps to happiness when you solve a linear equation understood in one variable. Simplify each side separately. Isolate the variable terms on one side, then isolate the variable, and then check. Now you say, well, wait a minute. How do you isolate a term and then isolate it again? Let's look at what we have up here with this problem. Okay, Debbie. 2x plus 2 equals 8. This was isolating the term containing the variable. But there's what? A coefficient. So then I did what? Either divided both sides by 2 or multiplied by 1/2. Now the variable is isolated with an implied coefficient of 1. So this, in a sense, shows the process. You isolate the variable, the term containing the variable, and then the variable. Then what would be the next step according to the 4 steps? The check, which means you'd say 2 times 2 plus 2, and you're asking the question, do I get the same number on both sides? 3 is the solution. Thank you. So I have the 3, and I would have been in trouble quickly because I had a 6 coming up here and not an 8, and I would have known immediately I screwed up. This becomes 6 plus 2. That gives me an 8. The 8 is equal to 8, and so I have a solution. So in a sense, we're asking the question, do we get 8? Now, this brings up a dilemma for us. How important is it to check a solution? In these problems, the only reason for checking a solution is to make sure that you've done the steps properly. But very soon, we get to a point where you do the steps properly and you really don't have a solution. Now I'm going to illustrate that with something that's a little bit ahead of us here for a moment. but it's worth a shot. Okay, I'm going to start, and Debbie, what I'll do is go to the sideboard after that box plot, and I'm going to try to limit myself to just what's left. I'm going to start a very simple problem. It's one that you're probably comfortable in doing, but it involves a square root. Okay, I'm going to sort of work backwards in something here. I'm going to look at a problem like, say, x is the square root of 9, and I'm going to show you something that gets you trapped. But as I do that, we're going to come back to these 4 steps here, just to leave those up on the board while I make the transition to the other side here. I'm going to write this expression, which I think is hopefully pretty easy for you. X equals the square root of 9. Now this is out of arithmetic. From the standpoint, the square root of 9 without a symbol in front of it implies what? That it's what? No. That it's positive 3. The answer that was given was 3 times 3, but negative 3 times negative 3 is also 9. So the question, if I want the square root of 9, this is called the principal root, and the square root here is supposed to be a positive value because I don't have a minus in front of it. But when you see something with a radical, one of the little tricks we're going to use is squaring both sides. So if I square the left side, I get x squared. If I square the right side, I get 9. Now to do a problem like this, most of you would be inclined to say, well, it's the square root of 9 then when I solve it. But I'm going to go a little bit further. I'm going to rewrite it this way. This is actually a process that we go through as we continue into other chapters. This is now a second degree equation in one variable. Not a first, but a second degree. You see the exponent. So we call this a second degree equation. The process that we go through here is going to be called a factoring process. And I'm not going to go into that process per se, but I will indicate to you, out of this, we will get a solution which will say that x is equal to 3 or x equals minus 3. Now the process of squaring both sides introduced a new solution to the problem that doesn't satisfy this. Now if you check both values, put a minus 3 in here, you get minus 3 on the left side, but this says you have a positive, the square root of 9, and this would imply that negative 3 is equal to positive 3. That's not true, so we consider this a root that's not valid. Root and solution mean the same. So the root, okay, or the solution are the same. This was a square root. And the point is, we check here by necessity. This was not a solution. We have to check solutions sometimes. Now, let's come back, Debbie, with camera 1 to 2x plus 2 equals 8. Okay, I want the front board 2x plus 2 equals 8, and I'm assuming you're going to be able to do that with camera 1 here. Now, if we come back to that equation, 2x plus 2 equals 8, I don't know that when I get down to x equals 3, I feel any great compunction to check the solution. I mean, we can end up doubling your homework just by checking solutions in every problem you do. And I'm a little bit concerned about that it gets too tedious. So I'm not going to be looking for the check of every answer. I want you to go through the first 3 steps. Later on, I will get very picky about checking solutions because then it becomes important. And if I get a value that's incorrect, it's referred to as an extraneous solution, an extraneous root. And if you give it as an answer to your problem, you're going to be wrong. When it's necessary to check, we should. Right now, I think it's overkill, and I'm not going to push it. So let's look at the 3 steps to happiness now. Coming back to the document cam. We're going to, let me bring that down just a little bit. There's now 3 steps. Simplify, isolate, and get the variable by itself. That's our guide. So coming off there. There's a couple other minor points here that you have to be careful of doing, and the text has done a very nice job of cautioning when necessary, giving you insight, and it's worth paying very good attention to such areas. Page 99. Here's a one that says, be careful with signs. Now what's involved here is a minus sign in front of a parentheses. What is understood with that minus sign technically? That there's a minus 1. The 1 is in front of the parentheses. So you could say I have negative 1 times that, and then you can do what? Use the distributive property and say I'm going to have 8 minus 3 minus 2a. Now we could argue, I'm then going to come to the sideboard, we could argue and write a general statement that says the opposite of a plus b is going to be what? Negative a plus negative b, or just write it as minus a minus b. That's understood. How do you defend it? Well, think of a distributive property. This minus is the same as minus 1 times a plus b, and now minus 1 times a is minus a. Minus 1 times b is minus b. It's a small point, but it's one you have to be sensitive to. Then there are similar such things involved, as we go off that for a moment, to other places, such as this one's at the top of 101. These are just sort of warning flags. When clearing equations of fractions, you multiply both sides of the equation by the same thing. So let's come back to a problem that we started on. Okay, let's cut to the document cam. There's my original equation. What could I have done with this first step to get it in an easier form? Get rid of the denominators. I could have gone ahead in that problem, and I could have, let me just bring this up to here. Now, bringing it about that far, I could have multiplied everything by 5 and said 2w minus 30 equals 7w. Get the idea? So multiply both sides by the LCD, which in this case is 5. That gets rid of the fraction, just like we talked about getting rid of a decimal by multiplying by 10 when we had tenths. Is it a good idea? In a sense, it avoids working with fractions, and folks, there is an advantage there. So if I looked at this first problem and did that first step, let me write it in first and then we'll cut to it. Here's what it looks like. Now I have 2w minus 30 equals 7w. Then if I bring the 2w to the right, subtracting 2w from both sides, what would I get? Minus 30 equals 5w. So let's come off there for a moment. So I have minus 30 equals 5w. Back to the document cam. Then you do what? Divide both sides by 5 and get minus 6 equals w. Okay. Is that easier than what we did as we come back to the document cam? Not as messy, right? Now, some people don't like fractions. Period. End of story. And I'd say my experience over the years working with students is that most students are intimidated by fractions and avoid them when possible. So if you don't like fractions, get rid of them legally. Okay, another caution. This is at the middle of 101. To avoid errors when multiplying terms like the following by 100. Now, what is the point of multiplying that term by 100? Clear the decimal point, correct? Now, there's a very important issue here that you have to be cautious on, and let me again, I'll come to the sideboard on this, and that has to do with that problem. I'll just use that problem as the vehicle, but it's one that you've got to be careful just a bit longer. Thank you, Debbie. I should have memorized that and didn't. Now, if you put 100 out here, And you're going to multiply by that. And by the way, there better be something over here that you have, because you have to do the same things to both sides of the equation. If you only do it in the left side, you've made an error. This is just like a fraction. If you do it to the denominator, you do it to the numerator. You do it to the left side, you do it to the right side. Is there an implied something on the right side of this that I should be doing? No. Okay, we'll put it in. Let's say that I have that this must be equal to 0.65. Then what would I have to do? Multiply the right side by the 100 also. That has to be understood. Now here's where the glitch comes in. You're only multiplying these two together. You're not applying the distributive property yet. Okay? This is an associative property involved here. There are three factors. I'm going to put brackets here. That's A, B, and this is C. That whole thing is C. So when I multiply 100 times 0.10, it has nothing to do with this part yet. So this becomes 10 on the left side. That then gets multiplied by the 20 minus t, giving me 200 minus 10t on the left side. The right side becomes what? 65. So I have 65 here. Now what happens? Well, I want to isolate the term containing the variable, which is negative 10t. So what am I going to subtract from both sides? 200. So that gives me what? Okay, negative 135. Then I divide both sides by negative 10 and get t is equal to 13.5. Now where is the problem? Right up here. You multiply here only the one time. You then don't multiply the 100 times this also. Now there's a nice group of problems from number 35 to 40 that I'm not going to assign as part of your homework in 2-1, but 35 through 40 are a set of 5 problems trying to hit this home. Your difficulty in doing the algebra in these introductory sets of problems is going to involve not making mistakes. Now, there are different kinds of mistakes. There are mistakes of logic, doing the wrong thing. There are also mistakes where you just added 2 numbers and got something that, otherwise you took 2 times 3 and your head was adding and you got a 5 when you should have been multiplying. That's not an error in logic, that's just a DAE, dumbass error. Now, there are errors in logic where here you say I take 100 times this and 100 times this. That's misunderstanding a distributive property, and that is a serious error that you've got to avoid. The DAEs, that's when you want to do something and you've got the right idea and your head's not connected to your hand temporarily. And I do these quite often when I'm reading ahead. My mind is responding to what my eyes are seeing, even though I should be writing a different number. So if I'm looking at this and I see negative 10t equals negative 135, and I've already divided in my head, I'm liable to write 13.5 there because I'm one step ahead where my hand should be. That's a different kind of error. By the way, note, these were both negative, so when I divided by negative 10 on both sides, I got a positive and a positive. Watch your signs. Enough there. Yes? Okay?
Can you have, well, before you put those brackets there, could you have done 10 times 20?
Okay, what you could have done is multiply 0.10 times 20 and then 0.10 times negative t, but then that's getting yourself into a more complicated problem because now you have negative 0.10 t. The idea is to avoid that darn decimal right out of the gate and avoid the possible error. It's not a bad thing to reference. Yes?
Okay, but what they're saying here, the error is different than what you just did. Did I miss?
Are we on page 101, clearing parentheses, and what they were talking about? Okay, there's a different issue there.
Sorry.
There is one more issue I need to raise to you, and I haven't actually illustrated problems so much as talking about issues you may have, but this is the bottom of page 101, and this is where I've got to end today. Recognize when there are no solutions and when there are infinitely many solutions. Okay? So this is that objective number 3. Recognize equations in which there are no solutions and in which there are infinitely many solutions. Okay? So this problem that's illustrated here is one that's sort of a no-brainer. Can we come down to that statement again? And can you hold on, please? We still have a class going in here. So if you'll just wait for a moment, we'll finish up. Thank you. So we have 5x minus 15 equals, and I have in parentheses 5 times x minus 3. Now, as we look at this problem, if I want to solve this, is it fairly clear that all I've done is illustrate the distributive property? The left side's what you get if you use the distributive property. And we know that that holds for any value of A, B, and C. But my point is, if you solve this, you get 5x minus 15 equals 5x minus 15. And if you proceed, you end up, next step, 0 equals 0. Now that's true for any value of x. So we would argue that the solution set is the set of x such that x is contained in the real numbers. That is considered, I don't know if I can pull that off, an infinite solution set. Okay? That's an infinite set for a solution. Okay, so that's the first part. Now, I don't know if he illustrates the next part where you have no solutions, but that's one with infinitely many solutions, and here's one where you have no solutions. This is on page 102. Let's see if I can again get that clean, and here is my original equation. Let's go for it. 2x plus 3 times x plus 1 must equal 5x plus 4. Now, this has been rigged like crazy because if we come back to it, and we're just going to do this in our head because I want to bring closure here pretty fast. Closure in a different sense than we've talked about with numbers. But do you see where you get 5x here? Plus 3 is supposed to be 5x plus 4. So let me leave that up there. And so what we're going to get is a statement out of that that says 5x plus 3 is equal to 5x plus 4. Now, what you're going to do is subtract 5x from both sides, and that says 3 equals 4. Well, that's a nice try, but 3 is not 4. There is no value that will make this statement a true statement. Remember, this equation at the beginning and the solution I have are equivalent equations. The solution for here must be this solution. Nothing works here, nothing works there. So this solution set is known as the null set. There is nothing in that set. It's a 0 with a line through it, meaning the null set. That's a very important observation. The homework with the exclusion of 35, I'm sorry, Debbie, that was bad for me. Okay, we have this exclusion. Do not do these. So 35 through 40 we don't do, but we do cover 1 through 60 odd in 2-1, with the exception of that 35 through 40. So 2-2. Did I say 2-1? Bad. 3 errors in a row. Okay, section 2-2. 1 through 60 odd, but do not do 35 through 40. Okay, we started with Buddy Holly. We're going to close with Buddy Holly. What's your choice, Debbie?
Every day.
Everyday algebra, you bet. Have a great day.